The most readily measured property of a gas is pressure. And the SI unit that we use for pressure is called the Pascal, which we represent with a capital A, or capital P, lowercase a. Okay. So how do we get this unit, the Pascal? Okay, so to derive this, we got to go back to physics a little bit. So remember that when we calculate velocity, this was the change in position over the change in time. Or if we were going to do this unit, to measure the change in position, this is meters, okay? The change in time, that's measured in seconds. So the units would be meters per second. Now, if we were to calculate acceleration, this would be the change in velocity over the change in time. Or meters per second for the change in velocity divided by time, the change in time, which would be seconds, or meters per second squared. Okay. Now, according to Newton's second law of motion, force is defined as the product of mass times acceleration, or F equals ma. Now, the unit that we use for mass is the kilogram. Okay, so let me put that in. And the unit for acceleration is meters per second squared. So we get for, if we multiply these together, we get kilogram times meter divided by second squared. Now, 1 kilogram meter per second squared, this is equal to a Newton. All right, so we've got now our force, the Newton. Now, where 1 Newton is equal to 1 kilogram meter times divided by second squared. Now, finally, pressure is defined as the force divided by the area, which force we measure with the Newton, okay? Area, that's going to be meters squared, all right? Now, 1 Newton per meter squared, this is the Pascal. So that's how we derive the Pascal. Now, are you going to have to go through this derivation on the exam? No. But this one's a cool one to show you where this unit's coming from. Okay. Now, all gaseous atoms and molecules are affected by gravity, and they feel a gravitational pull. And because of this, the atmosphere is going to be denser near the surface of the Earth and at higher altitudes. And the denser the air is, the greater the pressure it exerts. Okay. Now, atmospheric pressure is defined as the pressure that's exerted by Earth's atmosphere. And to measure this, we use a barometer to measure atmospheric pressure. Okay. Now, originally, way back in the 1600s, the way a barometer was created was kind of like this, where you had a dish, okay? And inside that dish, you had a pool of mercury. And what you did was take a glass tube, turn it upside down, and put the open end at the bottom of this dish, closed end on the top, okay? And then the mercury would run through this column. Okay, and it turned out that if you measure the distance of where the pool ended up on the dish, so if you start there and measure to the top of that column at normal pressure, normally that distance should be about 76 centimeters long. Okay. And sometimes, depending on whether a warm front or a cold front's going through, if it's storming, if it's sunny, whatever, sometimes these numbers could it could go up, could go down. It all depends. Okay. But this was the original barometer. Now, since then, we've gotten away from this because open mercury to the environment is not very safe and it's not very environmentally friendly. So we use ethyl alcohol a lot of times in our barometers. But this is what it looks like. Okay. Now, the standard atmospheric pressure The standard atmospheric pressure, the way we define this, this is the pressure that supports a column of mercury that's 76 centimeters high at 0 degrees Celsius. So this is the pressure that supports a column of mercury that's 76 centimeters high at 0 degrees Celsius. Now, it turns out this number, 76 centimeters, this is the magic number, because if we convert this to millimeters, that gives us 760 millimeters of mercury. And so this, by definition, 760 millimeters of mercury, this is equal to 1 atmosphere, or ATM. Now, even though we use a Pascal, that's the SI unit, we're still, in chemistry, we're still stuck on ATM. So we still measure everything in atmospheres. Now, there's also another unit. The guy that was working on pressure, the guy that was originally studying pressure and he discovered his findings, his name was Torricelli. Okay, and so he came up with his own pressure system. He said that 760 millimeters of mercury, or 76 centimeters, this would be also equal to 760 torr. So you may come across the torr unit, and just remember, that's like saying the same thing as millimeters of mercury. Okay, now how does atmospheres compare to pascals? Well, it turns out that 1 atmosphere, so normal atmospheric pressure, okay, this would be equal to 101,325 pascals. All right. And if we could write this, since it's a SI unit, that means we could write this as convert this to kilopascals. So 1 atmosphere would also be equal to 1.01325 times 10 to the second, 10 to the second kilopascals. Okay. So we can use a barometer to help us measure atmospheric pressure. We can also use a manometer to help us measure the pressure of other gases that are other than the atmosphere. So the way this works, you've got a U-shaped tube, but on one side of the U, you've got a container that holds a certain gas of interest. Inside that tube, you've got a pool of mercury. And so again, what you're doing is that based on the pressure of this gas, it's going to give you you're going to measure the length of this column of mercury, and that's how you define the pressure. Okay, now that we talked about pressures, let's talk about how all the individual gas laws that got us to what we know about gases today.